Good morning. Thank you for joining us on this presentation, which addresses some of the results of the Interreg Europe project Zero CO2, and it concerns the use of technology options to improve energy efficiency and reduce carbon emissions in buildings. It is a summary of 20 years of research at the University of Malta for testing different systems and different building envelope improvements, and therefore you will be seeing today real case studies results of certain areas that are fit and useful for Mediterranean climate. With regards to the building envelope, we are speaking about wall and roof insulation, double glazing and shading. While for services and renewable energy, we are focusing on water heating, photovoltaics, and on space heating. One of the first projects that was carried out at the Institute for Sustainable Energy was to evaluate the level of improvement of insulation to walls and how this impacts the energy performance of different dwellings. As we know, in Malta, many or most of the buildings nowadays are flats, and therefore this project is focusing on a building block of 4 apartments on this 0 floor, first, second, and top floor. We can see that if the U value of single walls buildings is improved from 1.57 to 0.5, the energy performance of these flats improved tremendously, from 6% up to a maximum of 30% for the second floor. And this calls for better insulation of walls up to the value of 0.5 watts per meter squared Kelvin. For the ground floor, and given that it has underlying garages, it is also important to insulate the floor because it gives an added savings of 15% on the energy performance. With regards to the second floor, because the penthouse recedes about 4 meters from the facade, part of the roof or the ceiling of this second floor is now a roof, and it's exposed to external conditions, and therefore insulating that part can also give a small improvement of 2%. What's interesting is that because many buildings in Malta, dwellings have a low window to wall ratio, roughly about 10% glazing only, the improvement if one implements double glazing is quite small compared to the improvement in the insulation of walls. If one goes to different buildings like hotels, another test was carried out, another research was carried out, and we can see that the improvements in insulation of walls gives roughly 6%, which is lower than dwellings. The main reason is because the perimeter to floor area ratio is small in these buildings. If we go to offices, in this case, this is a fully detached office, we can see that better insulation of walls yields even better results, especially for heating and cooling demand of 36 and 44%. If we apply insulation to walls and roofs in schools, we get an improved performance, but given that most of our schools are already built to a very good insulation level, according to the minimum energy requirements of Malta, the added benefit will mostly become because the students will feel warmer, especially in winter, while in summer, given that the schools will not be operating, the benefits can be assumed to be negligible. With regards to roof insulation, we can see from our results and research that the existing minimum energy requirements of having a roof U value of 0.4 watts per meter squared Kelvin is sufficient, and there is no need for added insulation. Mind you that the insulation of roofs only affects the top floor apartments. And therefore, to sum up the wall and roof insulation research, we can say that at the moment we have a support scheme, financial support scheme of 15% on the cost of insulation, but there is no wall insulation support scheme in the country. And therefore, with regards to the zero CO2 project, we propose that there should be sector-focused incentives, for example, wall insulation for dwellings or roof insulation for existing large roofs in industry and even in hotels and other commercial buildings. It is also important that the roof insulation subsidy is revised, because at the moment it only caters for the value of the insulation itself, but not for the retrofitting costs that are usually extensive. When we look at double glazing and shading, this is one example of an office that has extensive glazing. The left part of this diagram shows that the wall temperatures of the building before shading was implemented, while the right part shows the temperature of the walls. We have the east, west, and south walls after shading was implemented. The red dots shows the outdoor temperature, maximum temperature, while the green dots shows the minimum temperature. It's very clear that when on days when the temperature was very high outside, the temperature of the walls, especially the south and west walls, reached a whopping 37 degrees centigrade. For a similar day with such peak temperatures, after shading was applied, we can see that the wall temperatures remained almost constant throughout the period at a much lower temperature of around 32. Given that human beings are affected by a combination of temperatures, that of air temperature and the wall temperature, known as the operative temperature indoors, it is important not only to air condition the space, but also to make sure that walls are kept at low temperatures so that the operative temperature is more convenient. Other tests and research work carried out by master's students at the Institute for Sustainable Energy has shown that for offices, it is important that shading is applied as soon as the glazing to wall area jumps or exceeds 40%. One might ask why if the orientation of the office is southwest, the energy demand for heating and cooling is lower than when the office is oriented southeast. One has to realize in this particular example is that the operational hours is only from 8 till 5, which means that the simulations carried out only included this time period, and therefore the afternoon period when the sun is low in the sky was not taken into consideration because the office will be closed. When we look at the dwellings, the shape of the graph changes because dwellings are assumed to be occupied in the morning and also in the evening. And therefore here one can clearly see that for orientations due to southwest and southeast, these are the walls or the windows that require most shading. Once again, as soon as the glazing to wall ratio exceeds 60%, shading becomes effective. One also realizes here that even if one uses different types of U values for windows, the effect of heating and cooling demand is minimal until the glazing area becomes significantly higher, roughly 80 or 100% window to wall ratio. And this implies that when the external temperature or the external climate is mild, it is not necessary to go for very high performance glazing, but it's more important, especially for retrofitting, to introduce shading rather than changing existing windows. At the moment in Malta, there is a subsidy for changing single glazing to double glazing to the effect of 15% of the value of the double glazing only, but not of the frame housing the glass. Within the framework of the Interreg Europe Zero CO2 project, we are proposing that double glazing schemes should only be given for large window-to-wall ratios and should also include support for changing the support frame into an insulated frame or some sort of frame that has high efficiency with regards to U value. There is a need to encourage shading, and hence, given that the shading elements could be expensive, a support scheme can help to encourage, especially homeowners, to install external shading to their fenestration. One can also suggest that for future improvement of technical guide F for minimum energy requirements, a minimum shading of 50% is included as mandatory. Now we go to systems, and here we can start with the air-to-water heat pump, which this example here shows a large one with about 300 liters of storage tank. Very good, very suitable for a restaurant. And we can see that tests carried out show that a high COP of 3 has been achieved throughout the months of winter and even spring. This implies that in comparison to a normal electric resistance heater, such heat pump can save up to 65–70% of electricity for heating water. We can suggest that such heat pumps are very adequate for heavy consumers of hot water, such as restaurants and hotels. But also we need to make sure and encourage users and sellers of these heat pumps to avoid operating the heat pump in a cycling mode around the set temperature, because if this happens, then the COP drops even below 1, according to the tests carried out at our institute. Another type of heat pump using a solar-assisted thermodynamic panel, as seen here on this roof, can make use of the energy from the air as well as solar radiation to absorb into the water tank here below. Again, we can see here a superior COP in the winter season of even higher than 3, reaching up to 4.4 around January, February. Once again, it is important for a climate like Malta, where solar radiation in summer can be very high, that the panels connected to these heat pumps are not oversized, because this would lead to low COP during the summer period. Ideally, a heat pump of this sort should be operated at night during the summer period, because the energy from the air is sufficient to heat the water and keep the COP at a high value. As a conclusion for this thermodynamic heat pump, we can see that it is very attractive, especially in the winter and the spring seasons, but one has to be careful how to use it in summer. With regards to existing support policies in Malta, the most recent incentive given to heat pumps for dwellings only was introduced in October 2017. The level of support is the same as that of a solar water heating of 40% on capital cost up to a maximum of €400. Within the framework of zero CO2 and after discussions with many stakeholders, including policymakers, it is clear now that there should be a sector-focused incentive for introducing heat pump water heaters in Malta, starting with the highest consumer of hot water, such as sports complexes, restaurants, and hotels. Also, it is important to ensure that these heat pumps have some sort of control to avoid cycling around the set temperature during the day. Now we move on to space heating, where we can see that an infrared heater can have some advantages over a heat pump. The graph here shows one test carried out on an infrared heater in red, and we can see that for the same set temperature, the infrared heater can heat the room to a higher temperature than a standard electric resistance heater, with the result that the user will opt to lower the set temperature to bring the red graph down to the blue graph. In doing so, energy is saved. When compared to an air conditioning system, a heat pump with a blower, we can see that the air conditioning system circulates the air in the room with peak temperatures that are well beyond comfort levels in winter. This cycling is caused because of the thermostat settings. And therefore, as a conclusion, we can say that infrared heaters can have better performance with regards to energy efficiency when compared to an electric resistance heater. It also has health benefits because it does not circulate the air and it does not move dust particles in the air as air conditioner systems do. It is very useful for large halls or in schools where many people congregate because it gives a warm feeling, given that the heat is transferred to human beings through radiation only. At the moment, there is no awareness on these new heating modes, and there are no schemes for financial support, and therefore within the Zero CO2 project, we recommend that the infrared heaters are given more importance and more studies are to be carried out to see if they really save energy in all sectors. Now we shift to photovoltaics. Extensive testing has been carried out by myself and many other students under my guidance and the guidance of other professors at my institute since 1993. And one of the tests carried out here, we can see that as the costs of photovoltaics drop, one can afford to lower the angle of inclination of photovoltaic panels in order to squeeze in more PV panels and therefore produce more energy per square meter of rooftop area. The graph on the right shows the output to be expected from a PV panel on a sunny day if the inclination is dropped from the ideal angle of 30 degrees to horizontal and even vertical, which is useful for facades. Here we can see that the 15-degree pink graph is slightly lower than the ideal one, and hence one could easily consider reducing the angle from 30 to 15 degrees, and this will not impact heavily on the overall output of the solar panel. This is also shown on the left-hand side when we compare 30 degrees to 15 degrees. So we can see that the monthly outputs, the blue one is for 30 degrees and the pink one is for 15 degrees. We can see that during summer period, the output of both inclinations is roughly the same, while it drops considerably only in winter. But remember that in winter we have only 1/4 of solar radiation of that in summer, and therefore the overall losses are not significantly high. One can also speak about the vertical option of putting PVs on facades, which still has to become more popular in Malta, especially because we have more flatted dwellings and buildings. And we can see that this has a positive effect because we have higher output of photovoltaic electricity in the winter season, reaching almost 100% capacity of those solar panels. Other research groups within my institute has carried out tests on existing photovoltaic modules that have been in operation in Malta for the past 30 years, and the overall result showed that PV degradation in Malta will be around 0.91 plus or minus 0.05% per year. This is important when one plans to introduce renewable energy targets in the country, whereby in the case of Malta, it is heavily relying on photovoltaics to achieve the 10% renewable energy target for 2020. In this case, one has to ensure that PV systems installed years back will be replenished by new PV systems so that the final outcome in 2020 will match the output required for the RE target. Real PV systems were also tested in different zones in Malta and Gozo, and we have seen that the real operation is roughly the same for all these systems. The highest was achieved in Gozo, where the climate is cooler and cleaner, and that was an average of 4.74 kilowatt hours per kilowatt peak per day. Other systems that had some partial shading from wall perimeters around the roof had a drop of 4% when compared to the ideal situation. And others that have also cross shading from one row of PV panels on the others, besides the partial shading from the roof perimeter wall, had suffered 8% degradation compared to the ideal situation. The existing policies in Malta are favoring photovoltaics. There were very strong capital grants since 2006, and today we have at least 100 megawatt peak installed in the country. A new scheme by government to encourage homeowners to invest in photovoltaics, especially those that have no access to rooftops, has been successful and is moving in the right direction. However, there are no solar rights given to homeowners with a rooftop, and therefore one has to carefully consider any possibility of giving a minimum solar rights, not only for installing PV panels or solar water heaters, but also to have a minimum amount of sunshine on these rooftops with regards to well-being and health. It is positive to note that there are now PV installation standards that have been published by the Standards Authority, and most recently there was a solar farm policy published by the Planning Authority which encourages installation of large PV farms on derelict quarries and large rooftops. Within the framework of zero CO2, we are encouraging to consider PV on facades and make it even mandatory for new buildings, because this is the way forward how one can achieve near zero energy buildings by investing in renewable energy on site or nearby. And to investigate possibilities of having better protection for solar rights. We move now to solar heating. Extensive tests have been carried over the years. A typical operation of a solar water heater for domestic use can produce up to 1,600 kilowatt-hour thermal per year. This is equivalent to the same energy produced from 1 kilowatt peak photovoltaic system. The real-life operation test for a real system installed between 2012 and 2017 showed that the solar factor or how much energy is being consumed by an electric backup heater during days with low sunshine is equivalent to that consumed by a heat pump. We can see this in this graph here, in this table, where we can see that for the months between November and March, the electricity consumption as backup heating by a solar water heater for these weeks were minimal and were comparable to that consumed by a heat pump. The graph on the left-hand side shows that at least each solar heating system can give roughly between 3 and 4 kilowatt hours per day of thermal energy free of charge. A solar water heater tested between December and April 2012 to 2013 showed that the solar fraction is always high, as seen by the dark blue line. It reaches 1 in summer and roughly 50% or 0.5 during very cloudy weather, which normally occurs in autumn. During the winter season, the solar fraction goes up to 80%, and in January, February, it goes down to 60% or 0.6. So this is very positive. Given that this particular solar water heater was simulated to consume 4 showers equivalent to a family of 3 or 4 persons, the efficiency of this solar water heater was relatively low, in the region of 40 to 20%, as shown in the red line. This implies that the solar water heater has not reached its full potential because the demand for hot water was limited according to the scenario of a family of 3 to 4 persons. Another test in a housing block has showed that the average hot water consumption per person in households is 30 liters per person. This gives an answer to a frequently asked question and helps designers and installers to install the right system for the right use and for the size of the family. In other words, one size does not fit all, and one has to design solar heaters based on the demand. Other tests have shown that a solar heater can improve the energy performance of buildings by up to 18%, and vertical solar water heaters are a viable option for facades on buildings because it favors the production of hot water in winter, and that's where hot water is needed most. The situation in Malta is that at the moment there is a financial incentive of €400 per household, but this has been effectively unchanged since 2006. And we believe that it is the right time now to reconsider this grant and probably to increase it to a higher level to cater for added changes that a homeowner requires to make to accommodate a solar water heater in an existing building. Within the framework of zero CO2, we are encouraging that only high-quality products are allowed into the market. We would like to see a combination of incentives, for example, PV solar thermal financial incentives, and it is also high time that a minimum percentage of hot water from renewable energy sources, such as solar heating or even heat pumps, is to be introduced for new buildings. As conclusions, we can see that over the past 10 years, a number of policies favoring energy efficiency have been introduced in Malta. Some of them were very successful, such as the PV grant, while others were not so successful, such as the solar water heater grant and the double glazing grant, as well as the insulation to rooftops. And these require revision. With regards to technologies, our research over those past years have shown that there are a number of technologies that are market ready and are suitable to lower the carbon emissions of buildings immediately. And they should be encouraged both in the new buildings and in renovated buildings. However, some of them could have technical weaknesses, but these can easily be tackled as long as the user knows about them. We have highlighted one particular example of heat pumps whereby it is not good for the user to allow cycling of the water heat pump around the set temperature, because the COP will drop even below 1. It is true that many technologies are still not cost effective, partly because the price of electricity in Malta is also cheap, and hence better support and incentives are to be given not only to homeowners but even to developers and designers, so that future buildings are built with integrated renewable energy technologies rather than retrofitted. With regards to actions, we encourage better incentives and revision of existing incentives, and these incentives should be targeted to particular sectors rather than focusing only on the housing and residential sectors. We believe that other sectors that are contributing valuably to the prosperity of economy in Malta should also be given support to enhance their energy efficiency situation. It is high time that certain energy efficiency and renewable energy technologies become mandatory with a minimum percentage, especially for new and renovated buildings. Thank you for your attention. And as you can see here, there are a number of papers that have already been published in the past. And for further information, you can refer to these publications, or if you wish, you can contact us for more support and for future collaboration in this topic. Thank you for your attention.